All right, actually, there we go. There's the beginning of the slideshow. Today we are happening to cover these next two sections. This is, by the way, Professor Iris Miano. Hello. Math 32 at SMC. We are going to be covering sections 3.6 and 3.7 regarding, in 3.6, relationships, somewhat in general, but particularly we're going to cover perpendicular lines. There's going to be the definition of this term and a very easy to confuse with the definition theorem, along with, myriad other things. And then finally, in section 3.7, we're going to have an overview of the formal process of writing the proof of a theorem. We're going to think about theorems in regard to what we've already previously learned about conditional statements. You can always rewrite any theorem as a conditional, and that's going to help us take apart the pieces of the statement in such a way that we'll be able to write it as a proof and given statements, and then we'll be able to start from the given and get all the way down to the proof step by step, and that's basically what writing a proof for a theorem is. Okay, so I believe we are in week 4, day 8. Yes, oh, how far we've come. All right, so let's get to it. Starting with relationships, particularly perpendicular lines, let's define this term. Perpendicular lines are two lines that meet to form congruent adjacent angles. You may notice off to the side here some new notation. There's a new symbol right here. In the figure, we have lines L and M, and certainly they're intersecting, although the point of intersection is not explicitly shown. But they are meeting. That's another way of saying intersecting. And they're forming congruent adjacent angles, which is to say that when two lines intersect, no matter if they're perpendicular or not, always 1, 2, 3, 4 angles are emerge from the intersection. So you get to say that angles 1 and 2, since they are adjacent to each other, they're congruent according to this definition. Furthermore, angles 2 and 3 are congruent to each other, 3 and 4 as well, and you can use the transitive property to link any of these angles to one another in a subsequent step. But this is kind of like the string congruency statement that gets to be made, starting with angle 1 and moving all the way around to angle 4. Okay? Now, this definition, I just want to make abundantly clear, is something that gets misused a lot. And by that, I mean there are lots of related concepts associated with perpendicular lines that have nothing to do with the definition. So there will be instances where I often see students erroneously using the simple phrase definition of perpendicular lines, and it's because they are linking the definition to other concepts that are technically not a part of this definition. So this is where I think it's really important to be careful with your internalization of these words and how they are linked up to certain theorems, but not confuse the theorem outcomes associated with these terms, most notably perpendicular lines. You'll just want to be careful, is what I'm saying. And please do note this new bit of notation. It's looking kind of like an upside down capital T. That is mathematical shorthand for the phrase is perpendicular to. So this phrase right here, this symbology that I'm underlining with my cursor right here, says line L is perpendicular to line M. So now we get our first theorem of this section, and it states if two lines are perpendicular, then they meet to form right angles. Now, if ever you want to state that some right angles are in play and the only thing that you're given, or you can only conclude at a present point that two lines are perpendicular, you can use this theorem in order to say that the angles created are right angles. But it's not the definition of perpendicular lines. You guys feel me on that? So here is a figure. It's a little bit of an offset a set of perpendicular lines. And since it was stated, so if I go back a slide here, let's just say you were only given this figure with the two lines intersecting and this statement off to the side stating that they're perpendicular. You can use this theorem to therefore conclude that all of the angles formed in the intersection are indeed right angles. Okay? Cool. So, again, I cannot stress this enough. It is very easy to confuse this theorem's outcome with the definition of perpendicular lines. Don't do it, okay? Make sure you keep those things distinct. Remember, what is the definition of perpendicular lines? They are lines that meet to form congruent adjacent angles. At no point in that definition were right angles mentioned. It's only with the incorporation of this theorem that you get to make that conclusion about what type of, angles you have. Okay, moving on from there to a general understanding of what a relationship is, or more concisely, a relation. It connects two objects of an associated set of elements. That's super broad, right? So what are some examples of relations that we might come into contact with in this curriculum? Well, and I just lifted this example, this chart right out of the book. So if you've already skimmed this section, this will look super familiar to you. We often use this fancy R to indicate a relation, and some examples of relations that you've already become intimately familiar with in your mathematical journey is equal to, greater than. Some ones that you've been probably introduced or reintroduced to recently are perpendicular to, complementary to, congruent to, and this is a non-exhaustive list, right? Certainly things can be supplementary, things can be not equal to, some, there's endless possibilities for possible relations are within the mathematical realm and otherwise. Objects being related according to these relations are, here are some examples of those, right? But these are not limited to just numbers, right? You could have variables equal to one another. So these are just examples of possible related objects. Certainly, congruent to extends further than just line segments. So as we've seen, angles can be congruent to one another, right? And so on and so forth. And here are some generic but more specific examples of these possible relations. Here's an equality, here's a greater than symbol, perpendicular to, that's a symbol that we just recently introduced, is complementary to. Here's some shorthand that is often used. I've also seen a big capital C as being a possible notation for relating two angles as being complementary. Similarly, the relation supplementary to could have like a giant fancy S in between the two angles named, indicating that they're supplementary to each other. We can talk more about notation about this in class if you like. And here's a statement of congruency between line segments, which is a relatively new notation for us. Okay, so let's talk about this relation idea a little bit further in the form of specific properties that relations could or could not have. Okay, so it's very common to in thinking about a particular relation. Let's talk about congruence of angles specifically. So what does it mean to be congruent in terms of angles, and does this relation have the following properties? So you might recall these from earlier in chapter 3, the reflexive property, which is just saying that anything is equal to itself or has the relation to itself that's being named, the relation being congruence of angles. So angle 1, right? Some abstract, not shown angle, just in your mind, go ahead and make up an angle 1. Is it congruent to itself? Yes, that is true. Any angle is congruent to itself. So this means, what we're trying to say here with this concept is that the relation of the congruence of angles has the reflexive property. All angles are congruent to themselves. And this is something that I kind of touched on a little earlier in a previous lecture video on how, like, why would we care about saying that an angle is congruent to itself? It seems so obvious and not helpful in any way, shape, or form. But it turns out, I'll kind of just very briefly reiterate my previous example in which I mentioned this. you'll want to have a way to link up an angle as being in a congruent pairing with itself if it exists within two separate triangles in the process of trying to prove that the triangles are congruent to one another or similar. Again, that is bringing into the conversation lots of concepts that have yet to be presented, so don't stress too much about this. Just understand that the congruence of angles relation is reflexive because all angles are congruent to themselves. Okay, now is the congruence of angles relation symmetric? Okay, so in order to entertain this idea, we would have to have two angles being considered, and if it can be shown that these two separate angles are congruent to each other, if angle 1 is congruent to angle 2, then it shouldn't matter in which order you name the angles, the congruency should still be in play, right? And that's certainly true. If angle 1 is congruent to angle 2, that means that angle 1 and angle 2 have the same measure. So you could certainly reverse the statement and contest that angle 2 is congruent to angle 1. It doesn't matter in which order you are presenting the congruency, it's still going to be true. And that is how we get to conclude that the congruence of angles relation is indeed symmetric. So you have two angles that are congruent to each other. You can say so in whatever order you want. That's what the symmetric property states. Now, is the congruence of angles relation transitive? So that's when you have three items in play, and two of them have to be connected, and then another two connected, and then the middleman is going to connect to the outer two. So here's a generic example using three unpresented angles. Let's say you have angles 1 and 2, and they are stated to be congruent. And in the same antecedent or hypothesis, as we'll come to call it in the next section, angles 2 and 3 are connected as being congruent as well. Well, it appears to me, if we're going to think about using this transitive property, we could identify angle 2 as being the middleman connecting angles 1 and 3 together, therefore correctly concluding that angle 1 must be congruent to angle 3. So yes. So the congruency of angles relation is indeed transitive, or it has the transitive property, we can say. All right? Now, not all relations have all three of these properties. And if you can think of even one instance in which it doesn't work, like come up with a counterexample, then you would say that that relation does not have that property. So as a fun exercise, the textbook has some interesting non-mathematical relations to entertain to see if they contain these properties. Now, there's not really a right or wrong answer with this kind of stuff. It's more or less a fun exercise, which is to say, okay, does the relation is in love with have a reflexive property, like consider one person, and it'll depend on the elements being considered, kind of, right? So you could argue either way that these properties are in play depending on what is being considered, which means that you don't necessarily get to say that the entire relation has this property. It might have to be a case-by-case basis, yeah, whereas previously in the is congruent to angle congruency relation that was just outlined, definitely those three properties, reflexive, symmetric, and transitive, were in play, but that might not be the case with more qualitative relations like this one in this example is in love with. So that is to say that if the relation is in love with has the reflexive property, then everyone is in love with themselves, right? Like every possible element in the people, right? If we're talking about this relation having the elements of people, then everyone would have to be in love with themselves. I would say that that's definitely not the case, for every single person. So I can't claim that this relation has this property. You feel me on that one? And furthermore, symmetric property, being considerate of two people, well, has it ever happened that person A is in love with person B, but person B is not in love with person A? It's like, the classic tragic love story. So definitely we cannot claim that the symmetric property exists for every pair of elements in this relation is in love with. And then think about the transitive property. If there are three people involved, if person A is in love with person B and person B is in love with person C, how likely is it that person A is in love with person C? I mean, unless you're in some kind of a throuple situation, I'd say that that would be highly unlikely, for sure. And it's not enough to, right, in this scenario, say, oh, it exists once, so the relation has this property. I would say that coming up with one instance in which it doesn't occur would be sufficient for you to state that the relation does not have that property, i.e., coming up with a counterexample is enough to quash the entire, connection there. Okay, so anyway, don't put too much, strain on yourself in going through the exercises that entertain non-mathematical relations in regard to these property considerations. It's just a bit of fun, okay? But I would love to talk about those in class if you guys are interested, for sure. I think it's a fun conversation, but it's not something that we need to be very heavily concerned with as far as accuracy of the outcome. All right, cool. Now let's get back into the meat and potatoes of this section with our theorems. So here is our second theorem in this section. So again, there's a very particular categorization in regard to the theorem numberings. This is the second theorem in section 3.6. I think I already kind of mentioned that. And it states, if two lines intersect, then the vertical angles formed are congruent. This is one that you're going to find is very, very helpful, and you're going to use it a lot in your future proofwriting. So here's a little illustration that I believe is already on your page, and so we're just going to add to it. So notice lines L and M are intersecting one another, and when they do, four angles are formed. And so I've gone ahead and labeled the angles 1, 2, 3, and 4 in a clockwise fashion. So what we get to conclude here is that since these four angles are formed by virtue of two lines intersecting, the vertical angles, which are across the way neighbors, are congruent to each other. So that'll be angles 1 and 3, since they're opposite of one another over the vertex for which the angles are formed. They are congruent, and same thing can be said about angles 2 and 4. They are another congruent pair of vertical angles, and vertical angles, of course, by definition, are formed when two lines intersect. They're in opposite positions, non-adjacent angles. Okay, great. So again, keep this theorem in your back pocket, but do much like we were I was saying earlier about the definition of perpendicular lines and that corresponding very highly related theorem. Do not confuse this with the definition of vertical angles, because if you recall, the definition of vertical angles are angles in opposite positions that are formed when two lines intersect, right? At no point in that definition do they say that vertical angles are congruent. It's not until we get to this theorem, which states vertical angles are congruent with two lines intersecting. That's what you get to use as justification for saying, in this case, that either angles 1 and 3 are congruent or angles 2 and 4 are congruent. I hope this distinction is clear enough for everybody at this stage, but if not, do not fret. We're going to see lots of examples of when it's relevant to use this theorem in our proofwriting yet to come. Okay, moving on. Okay, let's talk about perpendicular bisectors. It's all in the name, folks. It's lines that are perpendicular, and C bisects line segment BD in here. So thus, AC, the line that goes through the midpoint or the point that bisects the line segment, you can call it a midpoint, okay? The line that goes through the midpoint and is perpendicular, right? right? AC is perpendicular to BD. If it has those two features, then you can call it the perpendicular bisector. It kind of is a little bit obvious, but at the same time, you need to have both these items in play in order for a line to be categorized as a perpendicular bisector, okay? Great, so this is the definition of the term. It is a line that is perpendicular to another line and bisects the line segment on the line, okay, at the point of intersection. Cool. We are going to actually construct, I think it's a perpendicular, no, I think it's just a perpendicular line in the form of construction 5. That's going to be done in a separate video, so make sure that once you're done watching this video that you look for the construction 5 demonstration video. The instructions are on page 167. I'm actually just going to peek at those instructions just a moment. Yep, it's a construction for a perpendicular line, a line perpendicular to a specified line, so that'll be lots of fun. Okay, let's go ahead and fill out a partially completed proof, okay? We're still not at the stage where we are ready to write our own proofs from start to finish, but definitely you want to have some preview onto, you know, how proofs are structured, and we do that by exercising the completing of partially written proofs. So here, notice the bits that you have from the get-go, which are the given statement that angles 1 and 2 are congruent, and then separately, but similarly, angles 3 and 4 are congruent. Notice their placement in the corresponding figure. So we're going to use the figure and the given statement in order to draw conclusions and justify them until we get, oh, I'm sorry, this second line right here is also part of the given information. My bad, I forgot to specify that. So not only are angles 1 and 2 congruent and angles 3 and 4 congruent, but also angles 2 and 3 are complementary. So we need to remember what this term means in regard to being able to say, to conclude something about angles 2 and 3. We'll get to that in a little bit. And then we will be able to, use all of this given information in pieces probably, and then we'll be able to logically reason our way to the prove statement, which is that angles 1 and 4 are complementary as well. Okay, so here we go. Here is our partially completed proof. Notice that the very first statement is the first line of the collective given information. So what do we get to use as reasoning to justify that? Well, if it was given to us here, it's given to us there, okay? So always, if you're using the given information, and you always should use all of the given information in order to start your proof, then you get to justify it with simply the word given. It's kind of like your freebie, okay? Now, for the second statement, the thing that we get to conclude immediately after the given statement, it's going to be, you know, a two-parter. So I have question mark and question mark. So we got to figure out what those question marks are. We can look at the reasoning, the justification for that statement as a little bit of a clue. So the justification for this was that if two angles are congruent, then their measures are equal. So this is the definition of congruent angles right here. Okay, so I went ahead and did the safe thing and just wrote out the entire definition. That's what you will want to strive to do every single time. Just if you rely on just definition of congruent angles, you run the risk of using a term erroneously in regard to justifying a statement. Okay, so anyway, if two angles are congruent, then their measures are equal. Then it seems to me like I'm going to take these congruent angle statements and rewrite them as equal measure statements. Okay, so that would be the correct statement for number 2 there. All right, great. Notice that we are then, it looks like, kind of taking a sharp left turn and saying that angles 2 and 3 are complementary. Well, where did that come from? Because I was talking about angles being congruent and measures being equal, and then all of a sudden I'm like, oh, angles 2 and 3 are complementary? Oh, but wait, this is the second piece of given information, so I get to again say that this is given. See it up here? Angles 2 and 3 are complementary? So I'm simply stating the other piece of given information. And so this is a stylistic choice that the author of the textbook has made. Personally, I tend to put all of the given information, whether I'm going to use all of, some piece of it first and then use other pieces of it later. I just dump it all in the first statement myself, usually. Because technically you could break this first statement into two separate ones. They're kind of saying the same thing, though. But they decided to draw a direct conclusion based on just these pieces of given information and then introduce the second piece of given information separately. That's a stylistic choice, and you can choose to do that or not do that. You will find that when I present my own proofs, I will often, like I said, just dump all of the given information in the first statement, call it given, and then use it piecemeal after that. Okay. Now, notice that the fourth statement is unknown, but the fourth reason or justification is the sum of the measures of complementary angles is 90 degrees. That's the definition of complementary angles, isn't it? So if this is the justification, what would be like the, mathematical way that I would represent that? It would be measure of angle 2 plus measure of angle 3 equals 90 degrees, right? Because these two angles were categorized as complementary, so I'm using that definition to create this equation here. Now, notice that from statement 4 to statement 5, it's pretty much almost the same statement, but what's the difference? Well, the measure of angle 1 turned into the measure of angle 2 turned into the measure of angle 1. Ditto, measure of angle 3 became the measure of angle 4. Now what would justify that? So if you're thinking, oh, well, one thing just got replaced by another in two separate, instances, but it was one direct replacement of one thing for another. And look, earlier in the proof, I said that those things were equal. So it's totally fine for me to substitute one for the other. If things are categorized as equal in a previously established statement, then at any point it serves you later on in the proof, you can replace one for the other. So simply, the measure of angle 2 was substituted with the measure of angle 1, and the measure of angle 3 was substituted with the measure of angle 4. So I don't need to separate that into two separate statements. The textbook author also decided not to do that either. They just did it all in one go because these two substitutions, they're justified with the same term. They're just substitutions, so you can go ahead and just write it, as one statement, one action, and it has the same justification. Okay. Now, because this is a complete proof with just some of the things missing in it, we know that this sixth statement, since there's no seventh statement, is going to be the proof statement. So this is a little bit of a freebie for us, so go ahead and just put that proof there. But please read carefully the justification, the reason for the sixth statement, and recognize how it's justified. If the sum of the measures of two angles is 90 degrees, then the angles are complementary. So this is, again, the definition of complementary angles in the form of conditional statement. And so we're saying we're using this sum of the measures is 90 degrees business in order to categorize angles 1 and 4 as complementary. That's our proof statement. We have a complete and correct proof. All right. So there you have it. And if you're looking at this and you're like, oh man, I'm so anxious to write my own proofs from start to finish, that will be happening right now because we're in the next section. So this section 3.7 is where we finally really take apart the process of writing a formal proof of a theorem. And there are some elements of this that are going to be very familiar to you in regard to chapter 2 in particular. Specifically with everything that we know about conditional statements. Okay, so notice that initial components of a proof are given statement, or in statements there might be more than one, and then there's the proof statement, and sometimes there's also a corresponding picture. We'll talk about that in a second. So these statements can be combined and rewritten as conditional, in which the antecedent is the given and the consequent is the proof. Okay, so you could say if given, then prove, but the given and the prove will be like specific statement components. Now, since we're in a new textbook, chapter 3 is like the beginning of a new textbook like a different set of authors. Of course, they have to change the terms, but we already have introduced these items as antecedent and consequent, right? The conditional statement has those two components: if antecedent, then consequent, right? Now, in this chapter 3 stuff, they refer to the antecedent as the hypothesis, and they refer to the consequent as the conclusion. So if hypothesis, then conclusion. If antecedent, then consequent. If given, then prove. Those are all synonymous ideas. So just, again, to be clear, to connect all of the things that are equivalent to one another, the given statement, the antecedent of the conditional statement, and now the hypothesis of a conditional statement. Those are all the same thing. Given, antecedent, hypothesis. Same. Consequent, conclusion, prove. Those are all the same. One more time. Consequent, conclusion, prove statement. Those are all equivalent. And as stated before, the antecedent, the hypothesis, the given statement, those are all equivalent to one another. Okay? So as long as we connect all those things to each other, I think we can transfer over everything that we previously knew about conditional statements, i.e. the antecedent and consequent business. It's going to continue. The conversation is continuing about that. It's just the antecedent is now called the hypothesis, and the consequent is now called the conclusion, according to this new textbook's terminology. Okay, so here are some examples that we'll tackle in order to really make sure that we can take these conditional statements apart. We want to, state the hypothesis, capital H, and we'll call it capital H, and conclusion, call it capital C for the statement. Now remember, the hypothesis is the antecedent, and the conclusion is the consequent. So as long as we can identify those things that we have already been something that we've worked on previously, we'll be in good shape. All right, here is the example. If two sides of a triangle are congruent, then the triangle is isosceles. So what is the hypothesis here? Well, that's going to be the antecedent, and since this conditional statement is in the standard if-then structure, then the thing after if, but before the then, that's the antecedent, which is now called the hypothesis. So therefore, the hypothesis is two sides of a triangle are congruent, okay? The conclusion, I almost said consequent, the consequent of this conditional statement, the thing that's after the then, is now called the conclusion. So we're going to call capital C the triangle is isosceles, which is the conclusion previously referred to as the consequent. Okay, great. Now sometimes the example statement that you're given is not going to be having that if-then structure. So it behooves you to rewrite it as an if-then. So remember all those equivalent forms of the conditional, where if it was like, P implies Q, every P is a Q, if P comma Q, there was a whole chart, if you recall, in chapter 2. I forget what the table number was, but it had all of these equivalent forms of the if-then a conditional statement. So we want to rely on those elements in order to rewrite these into the standard if-then, and then it'll be easier to identify what the hypothesis, previously called antecedent, and conclusion, previously called consequent, elements are. So reword it as an if-then. So I would say every regular polygon has congruent interior angles can be rewritten in a standard if-then as if it is a regular polygon, then it has congruent interior angles. You see how I made that minor adjustment there, and it made it really easy now to identify who is the hypothesis, aka antecedent, and who is the conclusion, aka consequent. Here is the hypothesis, it is a regular polygon. The conclusion is it has congruent interior angles. Okay, so sometimes there might be an intermediate step of rewording it, the conditional statement as the standard if-then, but if you do that, the subsequent exercise of identifying hypothesis and conclusion tends to be a lot easier. All right, moving on. Okay, so here are the 5 essential parts of the formal proof of a theorem. There's the statement, which is sometimes the only thing that you will be provided with. And it comes in the form of a theorem, and even if it isn't in the if-then structure, you can always write it as an if then, okay? So, i.e. if, hypothesis, then conclusion, is the usual way it'll be presented, but not necessarily. From there, you can create a drawing, and that'll be a representation of the info given in the hypothesis only, okay? One thing that you want to not do, be very careful with in creating a drawing associated with a theorem, is to not incorporate any elements, that are in the conclusion, because you have to arrive there by, taking logical steps and justifying them along the way. All right, the hypothesis also gets turned into a explicitly stated given statement, okay? And by explicitly stated, I mean you will come up with elements, names for things, points, lines, things of that nature, specific names, so and that are linked up to your drawing, of course. The proof statement is basically the conclusion. It may need to be specified by specific elements that are either already kind of exist in your drawing or are yet to be highlighted by virtue of the writing of the proof itself. So, okay, there's those 4 elements, right? And then the 5th element is the proof. It's just it's listed as one single element in the essential parts of a formal proof, but this is by far the most challenging part of the writing of the proof. This is it. This is writing of the proof, like coming up with the chart and all of that stuff, starting at the beginning with only the given statements and the figure, and then reasoning your way all the way through to the proof statement. This is the crux of, the endeavor, and it's the most challenging part of all. A list of statements and reasons beginning with the given, ending with the proof. Okay, cool. So I believe you have this already written on your lecture notes. I don't think you're fiendishly writing this down right now, but if you are, maybe if you have extra things to write down with it, you can always press pause at any time. I'm sure that's terribly obvious and did not need to be stated out loud by me. All right, let's go ahead and tackle making a drawing for a theorem, and because sometimes you'll be asked to do this. So from the theorem, make a drawing. On the basis of your drawing, write given and proof statements for the theorem. So not only are we going to do this, but for this same drawing, proven, given and proved statements, we're actually going to write up the formal proof of it as well. So, but we'll start with the drawing. So here is the theorem. If 2 lines meet to form a right angle, then these lines are perpendicular. Okay, cool. Let's come up with 2 lines. Here's line PR. Here's line QS, okay? And I am drawing them in a way that makes sense according to where I'm going to end up, okay? So yes, they appear to be perpendicular, but that's precisely the thing we're trying to prove. So even though you want your figure to make sense as far as like where you're going to end up with it, you can't at this stage prove or assume that they are perpendicular. You're going to arrive there, reasoning your way through several steps, starting with the given information and ending with the proof statement. Okay, so the best we can do for now is come up with 2 lines, and they meet, right? Where do they meet? At point T. I didn't explicitly put the point, but I'm labeling it at point T. That's the name of the point of intersection, to form a right angle. So put a right angle inside the interior of one of the angles. I'm choosing to put it inside of the interior of angle PTS. You guys feel me on that? Okay, so now that I have specific lines and points that I've thrown into this figure, I am ready to write the given and the proved statements. Let's start with the given. Now the given should be, again, a formal reiteration specific to this figure of the hypothesis, or previously known to us antecedent. 2 lines meet to form a right angle. So I would say line PR and line QS intersect at T. This is them meeting. So these are my 2 lines. They meet so that angle STP, I'm calling it STP. I think earlier I called it angle PTS. Not a wrong name for this angle. It's just when I was writing this up, I guess I was thinking about it differently. Angle STP is a right angle. Okay? Great. So that is me imagining the antecedent of this theorem specific to the drawing that I created. Okay, cool. Now what would the proof statement be for this particular theorem? It would be these lines are perpendicular, but specific to the drawing. Which lines? Well, lines PR and QS are perpendicular. That's the proof statement, and since we have a symbol for is perpendicular to, we have a little bit of mathematical shorthand, we can make the proof statement incredibly concise. Okay, so now let's take all of these elements and let's write up the, hold on, sorry, the proof is partially given to you. I guess we're still kind of doing a little bit of hand-holding here. Earlier I stated, oh, we're going to write the formal proof of it. Sorry, I've already written up all the statements, so the exercise that I want to go through with you is coming up with all of the reasons, okay? All of the justifications for each step. And this is a complete proof. Notice that the first statement is the given statement and the last statement is the proof statement. But we can't just jump from one to the other, right? We have to reason our way through with definitions, postulates, and theorems that have been presented or proven beforehand, okay? So it's like we have a basket full of stuff that we've already learned, and from that basket we can draw in order to justify a series of steps that are going to give us the ability to go from the given statement to the proved statement. And here we go. So again, the statements are already written. This is a halfway completed proof. Our exercise is going to be justifying all of these steps. What is the first statement always going to be as far as reason, justification? It'll always be given to you, right? Because you always should be starting with what's given. And I did. Here's the given statement. I put it down there in statement 1. It's given. Done deal. Now, I say in the second statement that the measure of angle STP is 90 degrees. Well, what allows me to state that? Well, angle STP in the given information was categorized as a right angle. So I'm using a definition of a right angle, which I stated in its entirety. Right angles measure 90 degrees. That's the definition, right? Okay, so then moving on to statement 3, angle QTS is a straight angle. So measure angle QTS is 180 degrees. I'm claiming that this angle measures 180 degrees. It's a straight angle. Do I get to claim this? Yes, I do. I'm using the definition of straight angles, and I am using the figure. Okay, so one thing that I'm not sure I've made abundantly clear, oops, go back, you didn't see that, was that the given statement is what you get to use, but also the figure itself is part of the given information that you can draw from. So obviously angle QTS is a straight angle because these three points Q, T, and S lie on a line, right? So any points that lie on a line can be recategorized as a straight angle. And straight angles always measure 180 degrees. So you are using kind of the definition of straight angles in two separate ways in order to justify this statement, okay? Great, so hopefully that makes sense and is good. Let's move on to statement 4, where I state that the measure of angle QTS is equal to the measure of angle QTP plus the measure of angle STP. So QTS, the straight angle, is angle QTP measurement added to angle STP measurement. Yeah, they're, adjacent angles. So I'm using angle addition postulate. You guys feel me on that? When you have adjacent angles, sharing a vertex and all that business, well, by definition, all adjacent angles share a vertex and a side. So adjacent angles, you can sum their measurements to state the measure of the what you would call the main angle. In this case, angle QTS would be considered the main angle. Okay, so you can add up the angles measurements that form that main angle and create this equation. Okay, then from statement 4 to 5, it looks like we're doing some direct substitutions. You guys feel me on that? Earlier it was stated that the measure of angle QTS was 180 degrees right there in statement 3. And in statement 2, the measure of angle STP was stated to be 90 degrees. So substitution in two different places. We can do them both at the same time to use only one line of statement because they have the same justification. Then, what do we do? It looks like we are using this as an equation and subtracting 90 degrees from both sides to go from statement 5 to statement 6. So I would say that justification there would be subtraction property of equality, which I have shortened into the acronym SPO, subtraction property of equality. Again, I get to use this justification to go from statement 5 to statement 6 because it appears that the equation has changed in the subtraction of 90 from both sides of it. Okay, there we go. So then what? Oh, look at this. I am either, you could say, using the transitive property, it looks like, because I am saying the measure of angle QTP is 90 degrees, but so is the measure of angle STP. They're both 90 degrees. So we can set these two measures equal to each other. Or you could use substitution as justification, saying you're replacing one thing and then replacing another thing. Or since three things are involved, you can always use the transitive property to justify this as well. So I wanted to make sure that I mentioned that there's more than one appropriate justification for number 7. Substitution will work, but I see this also as an instance in which the transitive property is in play because the measure of angle QTP and the measure of angle STP are both equal to 90 degrees. So 90 degrees can be thought of as the middleman that links them together, transitive property style. But substitution is fine. You can claim that you have two instances of direct replacement. That's substitution. Okay, then we go from measures being equal to angles being congruent. What allows us to state that? Basically, the definition of congruent angles, which I have stated here using symbology. My justification or reason states for number 8, angles with equal measures are congruent. Sure, that'll do it. That is the definition of congruent angles. Then I have my proof statement. So I have angle QTP congruent to angle STP. And is that enough to say that they're perpendicular? Yes, because if two lines form congruent adjacent angles, then the lines are perpendicular. This is the perpendicular lines definition. So if I had stated in my reason simply definition of perpendicular lines, that would also be correct because this is the definition. Again, I'll read it again. If two lines form congruent adjacent angles, then the lines are perpendicular. These two lines, PR and QS, have formed congruent adjacent angles. And angle QTP, angle STP are congruent. They're adjacent to each other by virtue of the figure. So we've done it. We've fit the criterion of being perpendicular by using the definition. And that's it. So we have justified all of the statements in this halfway completed proof. But yeah, you are now starting to get the idea of how to write your own proofs, so that's something that you're going to start to do in this section. And then it's just going to explode from there in chapters 4, 5, and so on and so forth. Now, there are several theorems presented in this section, and some of them you're going to be asked to prove or partially prove, finish the proof, as some of your homework assignments. So let's introduce the theorems. Here there's the first theorem in section 3.7. If two lines meet to form a right angle, then these lines are perpendicular. We just proved this. That was actually the proof that we just completed in the most immediate previous example. Okay, the second theorem presented in 3.7 is if two angles are complementary to the same angle, or two congruent angles, then these angles are congruent. So I believe I have some figures for you on your lecture notes. So if angles 1 and 2 are both complementary to angle 3, then that means that they must have the same degree measurement, because that's the only way they're going to be complementary to the same angle. Because remember, the term complementary means that angles are summing to 90 degrees. So if two separate angles are summing up to 90 degrees with a third same angle, then they must be taking up the same amount of space, i.e. Having the same measure, i.e. congruent to each other, okay? And so when it says or two congruent angles, that is to say that in that scenario, you would have an angle 4 in the mix floating around, but it would have to be congruent to angle 3. And in that case, you could still use this theorem. Okay? So these are the things that I think you should add to your lecture notes right here, these complementary and congruency conclusionary statements. All right. Similar kind of a theorem here with the third theorem in section 3.7. If two angles are supplementary to the same angle or two congruent angles, then these angles are congruent. Okay, so here's the next very similar scenario here. Let's say we have angles 4 and 5 are both supplementary to angle 6, then that must mean that they have the same measure and are therefore congruent. Okay, so those are the statements I think you should add to your lecture notes, these right here. All right, so I'll give you a second to write those down. I'm going to sip some water. All right, a few more theorems to go, and then we'll be done soon. All right. Fourth theorem in section 3.7, any two right angles are congruent. Duh, right? Kind of a forehead slapper. But there's going to be instances in which we are really going to be happy that we have this theorem because it links two particular angles, right angles specifically in this case, together as a congruent pair of angles. And once we're in the stages of trying to prove triangles congruent or similar, we're gonna find instances in which this theorem is like super right on the money and very useful. The fifth theorem in 3.7 states if the exterior sides of two adjacent acute angles form perpendicular rays, then these angles are complementary. Oh, okay. So this one might be a little bit hard to visualize, so I definitely want you to draw a picture for this. I have the following scenario that I think is a pretty good illustration. Give yourself angle ABD and angle DBC. Now, if they are indeed adjacent to each other in such a way that ray BA and ray BC are perpendicular to one another, so they form a right angle, then ABD is complementary to angle CBD. They have to be because they collectively form a main angle that's 90 degrees. Therefore, they're meeting that definition of being complementary. Their measures have to sum to 90 degrees in order for this all to work out. Okay? Yeah, so that's what I would say would be a good thing to add to this particular theorem to illustrate it. Okay? Moving on. Sixth theorem in section 3.7, if the exterior sides of two adjacent angles form a straight line, then these angles are supplementary. So this is kind of like the supplementary version of the most previous theorem. So here's angle XZY and angle XZW. If they're adjacent to each other in such a way that they form a line, the line WY in this case is one such possible name, then the angles are supplementary to one another. They have to be because their collective measure has to sum to 180 degrees if they all are adjacent and the exterior edges form a line. Okay, great. So this is the thing that things I think you should add to this theorems area on your lecture notes. Cool. Moving on. The seventh theorem for this section, if two line segments are congruent, then their midpoints separate these segments into four congruent segments. Oh goodness. Okay, so give yourself two congruent line segments. I've gone ahead and drawn my line segments A, B, and D, E, and I am making a statement off to the side saying that they're congruent to each other. Okay, so I kind of forget if you guys have that already on your lecture notes or not. If you don't, go ahead and draw these. And then also, if you rely on construction 2 process, you can actually construct the midpoints on both of those line segments. But, for our purposes, you can go ahead and estimate where they are. And then state off to the side that C is indeed the midpoint of line segment AB, and F is the midpoint of line segment DE. So this is all the preamble. This is the stuff that you're presented with in this theorem. And so using this theorem, you get to conclude that the four line segments that are now in play are all congruent to each other. So that's AC, CB, DF, and FE. Those are all congruent to one another. You can line them up in a string congruency statement, and any combination of them can be linked up as directly congruent to one another. Okay, that's the thing you get to conclude with this theorem. And always with the conclusions of the theorem, consequent, what have you, I'm always going to precede that specific conclusion that is being made with whatever drawings that we have to illustrate our theorems, where I'm always going to precede that with this triple dot symbol, which I'm sure you already recall as being mathematical shorthand for the word therefore, and it's always going to introduce the concluding statement. Okay? I think this might be the last theorem. Let's see. This is the angles equivalent of the previously mentioned theorem, and it states if two angles are congruent, then their bisectors separate these angles into four congruent angles. So give yourself angles ADC and EHG, and state also that they're congruent to one another. Now, if you rely on, what was it, construction 4, that hopefully you've already seen the demonstration video for, you can construct with a high amount of accuracy the angle bisectors, which for angle ADC will be ray DB, and for angle EHG, ray HF bisects angle EHG. Okay, so then notice that with the incorporation of these angle bisector rays, we now have 4 angles in play. That's angle ADB, BDC, EHF, and FHG, or there might be other 3-letter names that are equivalent. In any event, they are all congruent to one another, and you may conclude by virtue of this theorem that this particular string congruency statement involving all 4 created angles with the incorporation of these angle bisectors. Okay, cool. So that's it for now. We are going to be in the next lecture video after the construction demonstration. You should definitely watch construction 5 demonstration video after this. But then beyond that, we're going to be starting chapter 4. Very exciting. Chapter 4 is more about parallel lines, and then we'll get into the indirect proof too. So exciting. Whew! That always throws students for a loop, that indirect proof. It's kind of like a little bit of mental whiplash. So look forward to that. And that's all for now, guys. So I look forward to seeing you soon. Bye-bye.